Hey everyone, welcome back to the channel. I hope you guys are doing extremely well. So we finished 1D DP and DP on grids. Now the next pattern of dynamic programming will be DP on subsequences. Yes, we will be doing DP on subsequences. Now a lot of times instead of subsequences, you might be hearing the name subsets. So either subsequences or subsets is what we are going to solve. So what is subsequences? Let's first understand the definition of that and then we can definitely move across. Now any contiguous or non-contiguous, that's very important. Any contiguous or non-contiguous part of the array is known as subsequence. Like for an example, if I give you an array like 1, 3, 2, then I can say 1 comma 2 is a subsequence because you see 1 2 is non-contiguous and it's following the order of 1 2. 2 comma 1 cannot be a subset or subsequence. We need to understand this. Whenever I say subsequence, it has to follow the order, right? Subset might or might not follow, but subsequence has to follow. Okay, so this is a subsequence. Again, is this a subsequence? Yes, this is also a subsequence because 3 comma 2 follows the order, as well as it can be called as a subarray. Subarray also you can call, and subsequence also you can call. Okay, so all the problems that we will be doing is based on DP on subsequence or subsets, and we will also be having one other stuff as target. Generically, we will be dealing with problems where we will be said ki, okay, this is the target. You have to pick elements from the array in order, like they will give some conditions in order to reach that target. So all the problems that relates subsequence, subsets and target will be the part of the next pattern we will be solving. We'll be solving a bunch of problems, and again I promise, the moment we finish the last problem in this pattern, you can solve any problem in this given pattern, right? So without wasting any time, let's get started with the first problem. What is the first problem? It states subset sum equal to k. So you're given an array list of n positive integers and an integer k. So you're given an array and an integer k. Your task is to check if there exists a subset in an array with a sum equal to k. Basically, does any of the elements combine to give you the sum equal to k? So if there exists, you have to return a true. Otherwise, you need to return a false. Like if you see in this example, we have 1, 2, 3, 4 and k is 4. I can say if I pick up probably just the 4, I'll get the summation 4. Or I can say if I pick up 1 and if I pick up 3, I'll get the summation as 4. So there are two subsets. And the question was if there exists a single subset. So the answer to this will be true. So that's what you have to solve. Okay, so first of all, how do you solve this problem? Now, obviously, we can't be writing a greedy solution because that will never make sense. We have to generate, like the first thing that comes to my mind is generate all the subsequences and check if any, yes, if any of them gives a sum of k. That's the first thing that comes to my brain. Now, how can you generate all the subsequences? There are two ways. One is the power set, and I've already made a video on that. You can definitely watch it. One is the power set, which uses bit manipulation, or the other one is the recursion. Again, the lecture 6 where we have discussed, or the lecture 8 of recursion playlist, the combination sum problem, where we have already discussed how to generate all the subsequences. But the question arises over here. What is the question? Does it ask us to generate all the subsequences? And the answer to that is no. So what's the question? The question states, does there exist a single subset? If I get a single subset, my job is done. So I don't need to generate all the subsequences. So that's where we think of, okay, so instead of generating all the subsequences, we just need to keep a check if there is any subset, right? So thereby we decide that, okay, we will follow the recursion method because we don't need to print all. We will just follow the recursion method. And hypothetically, when we just get one subsequence with the same subset target, we will return and we will stop. So that's my overall thinking. So we know recursion can help us to generate all the subsequences. And I've clearly told you what's the rule of writing the recurrence. Any recurrence can always be written in express everything in terms of index. Do we have an index here? Every array problem in DP will always have an index, and that's the array index itself. So we definitely have an index. Do we have any other parameter? On every index, we need to take care of the target that we are looking for. So we can say we definitely have a target that we are looking for. So always remember this. Whatever may be the problem on DP on subsequences and these subsets and target problems, we will always try to express everything in terms of index and everything in terms of target. Like in grid, it was I and J. In subsequences, it is index and it is target. Thumb rule. Okay, let's go to the second point. The second point is explore possibilities of that index. Now, what am I talking about? Let's understand. Explore possibilities of that index. So what am I talking about? I am talking about an index. And what the other thing? Subset or subsequence. So what can be the possibilities if you ask yourself for an index? Your brain will say, Striver, there will be two possibilities. Whether that array of an index is the part of the subsequence. Make sense? So I can say it's the part of the subsequence. Like array of index is the part of the subsequence. Or array of index is not part of the subsequence. Like logically only these parts will be there, not part of the subsequence. So I have two choices. One is it's the part of the subsequence, while the other one is it's not the part of the subsequence. So we have written all the possibilities. I don't see any other possibilities for a given index, right? We can think of the recurrence afterwards. Now what am I looking for? I'm looking for if any of them give a true, I'll return a true, because the question was return true if you get. So I'll be like, okay, if return true or false if both of the possibilities give. We will understand this in deep. So let's do one thing. Let's take so we have understood all the 3 points, right? Let's try to express. Now the question arises, how do I start with index? How do I start with target? Now always remember, what am I looking for? I'm looking for the entire array, and if there exists a subsequence with the target, whatever is given to you. So I'll try to express it in terms of f of n minus 1 saying in the entire array till index n minus 1. Hear me out properly. In the entire array till the index n minus 1. I repeat again. In the entire array till the index n minus 1. Does there exist a target? That is what the recurrence will tell you. In the entire array till index n minus 1, does there exist any target? For an example, if I'm giving you 1, 2, 3, 4 as the array, and I'm saying you the target as 4, if I'm writing f of 3, 4, that means I'm doing the indexing 0, 1, 2, 3, and I'm asking on this portion, on this entire array, does there exist someone with a target 4? That's what I'm looking for. That's the meaning of f of n minus 1 target. And this is going to be valid throughout all the DP on subsequences pattern. Okay, so we have understood this. So thereby we write, okay, f of index and we have a target. So that's the first thing, expressing the recurrence. So whenever we are expressing the recurrence, what are the base cases? I have to think about these base cases. What are the base cases actually? So my brain tells me, okay, Striver, what can be the base cases? The base cases is, it might happen we have achieved the target, because you might be at a state where the target is no more. Like initially assume over here the target was 4, and just imagine you took this 4 and you came out to this index. There is no further target to be achieved. Do you understand? So what I'm saying is, okay, I know one base case is for sure for the index target. So I'll be like, if at any moment the target becomes 0, I'll return a true. Why? Because we were looking for a subsequence which gives me the target as 0. So I've written that. So we have written the base case for target. What about the other one, index? So where is the call starting from? N minus 1. And we know we will go till the 0th index, because in an array, It's from n minus 1th index till the 0th index. So if you're standing at an index 0 and you have a certain target value, assume 4, can this target be achieved at this index 0? How can you determine? You can be striver. If the array of 0 contains the value 4, then this target can be achieved, otherwise not. Make sense? Because what does f of 0 comma target signify? It signifies till 0th index can we achieve this target, and if it's 0th index, it's only single element. So how can I achieve that target if it's the target itself? So thereby, if index is equal to 0, which is ultimately the base case, I will return true if the array of 0 is equal to the target itself. Perfect. So first step, express and write the base cases, is completed. Always, if you're writing a base case, first think about the target, then think about the index, think about the states. What can be the ultimates of states? What's the next thing? Okay, so what's the next thing? Explore possibilities of that index, because as of now you're standing at an index. So you are at an index and they're asking, can I form a subsequence from 0 to that index that gives me the target? Can I form a subsequence from 0 to index that gives me a target? I'll be like, okay, there are two ways. One of the ways is I say I will not take it. So can I say if I don't take it? Yes. Can I say if I don't take it, then the function will be, okay, I'm not taking that. So that guy is not taken. So I'll move to one less index. Always move back. And you'll say same target. So what does this signify? You were currently at this index, and from 0 to index, they were asking, can you form this target? Can you form this target? You said, hey, listen, I'm not going to pick this element. Thereby, I reduce it to this index minus 1. And I say from 0 to index minus 1, can I form the target? Because I'm not interested in taking this. So I reduce it and I say, okay, can I form this target now in the reduced portion of the array? I do a search on the reduced portion of the array. That's what this means. Make sense? It does. Okay. What's the other case? Boolean take. Let's keep the take as true. Sorry, initially false. I'll tell you why. When can you take an element into that? Now, if you're looking for a target, the target has to be greater than equal to that current index. Otherwise, how can you take it into the subsequence? Like for an example, if your array is something like 1, 3, 6 and your target is something like 2, you can't take 6 or 3, can you, in the subsequence? Because you're looking for something as 2. So I'm saying if the target is greater than the array index, then only take it, otherwise not. So if I take it, I will move to the previous index. Now let's understand what will happen to this particular target. Let's think about that. So what am I saying? I'm saying, okay, initially I had this recursion call. In this guy, can I achieve a subsequence that gives me a particular target? Now what am I saying? In this, is there a subsequence? I say, okay, let's say this guy is that part of the subsequence which I'm looking for. Let's say this guy is a part of the subsequence that I'm looking for. So I take this array of index and I say you're part of a subsequence. So if this guy is a part of subsequence, the target that I was looking for will now shrink. Because if initially the target was this big, it'll go smaller. Why? Because I've taken someone. And now I'll look for 0 to one lesser index in the shorter section of the array. And the target will go down by array of index because I've taken that into consideration. Now, either not take or either take. I'll just keep on trying. And the moment it reaches 0, if I can have this as the target, it will return me true or it will return me a false. Or if any of the moment the target is achieved, it will return me true. So there were two choices. One was the take, the other one was the not take. So I can say I'm trying two possible ways and I'm looking is there a possibility? Is there a possibility? So if I'm looking for is there a possibility, can I say it will be or of both of them? Because I'll try both the possibilities. If any one of them returns true, I return a true, because doesn't matter. If any of the possibilities give me a sum, I'm okay to go, because I'm looking for one subset only. So if any of them give me the possibility, I'm ready to go. And that's how your recurrence will look like in all the subsequence problem. Not take and take, not take and take, all the subsequence problem. You will be seeing that. So in order to understand this recursion better, let's do the recursion tree in the recurrence that we have written, so that you also try to see the overlapping subproblems if there are any, and then probably we can figure out if this recursion can be optimized or something else. But before that, we need to understand the recursion in depth, because this is the first problem on subsequences. So initially, where am I? I'm at this position, which is index 3, and I'm looking for target 4. So I say on this entire array, can I have a target 4? So I'm like, okay, let's take this guy. So if I take this guy, I'll go to index 2 with a reduced sum of 3. And if I say I'll not take this guy, I'll go to 2 and I'll be having 4. Which basically means is, I was saying, does this have a target 4? Now what I said, let's take this into account. So this took this into account. And now in this particular array, I'm looking for, can I have a sum of 3? Can I have a sum of 3 in this shorter array? And if I say I'll not take this, then in this array, can I have a sum of 4? That's what I'm looking for. So this is how I'm shrinking both of them. Perfect. Let's stop this and let's try to solve this. F of 2, 3. So again, you're having 2 and 3. You can take this one or you cannot take this one. Assuming you take this and assuming you do not take this. Okay. So if you take this, you shrink it to 1. And if you're taking the 1, you are left up with 1, 2. And if you do not take it, you are shrinking this to 1 and you still have 3. So if you take this 1, what happens is, now you're shrinking it to this and you're saying in this array, do we have a sum 2? Do we have a sum 2? Makes sense. Let's go across. We have something as 3. Now 1, 2 means in this, can I have a target of 2? Now comes the take wala if else. Can I pick this 3? Logic will say no. Why? Because this is 2. And I'm looking for a target of 2. How can I pick someone as 3? So the take condition will never be there. It will always be false. The take condition will always be false. I'll say not take. If I don't take, I'll reach the 0th index. Yes, I'll reach the 0th index and I'll be like, just a minute. Yeah. And I will be like, on the 0th index, can I have 2? So on the 0th index, can I have 2? Can I have 2? And when you reach the 0th index, you're having a target 2. Is it 2? Yes. So the 0th index itself can give you the target 2 that you're looking for. Thereby this guy returns a true. So f of 1, 2 was calling take, which gave him false, and was calling non-take, which gave him true. So you said, okay, non-take gave me a true, so I will return true. Now this f of 2, 3, yes, this f of 2, 3 sees that this is giving him true. And you can solve this f of 1, 3. But the moment it gets 1 true, it returns. Again, you can solve this, but there is no requirement of solving this. Since you got a true over here, this can also return a true. Now, you might ask, Striver, where are the overlapping subproblems? So if I would have gone deep, you would have seen, like in this case, if I would have gone by taking, it would have been f of 1. And second index was this. So this would have been f of 1, 3. And if I would have not taken it, it would have been f of 1, 4. So you see f of 1, 3 overlapping with f of 1, 3. So there will be overlapping subproblems for sure. So you saw how the recursion did work by taking and non-taking. So if we talk about the recursion time complexity, what will be the recursion time complexity? It will be we go of 2 to the power n, because for every array element, you have couple of options. Either you take that element into consideration, or you say, I'm not going to take this element. So you just have couple of considerations. So 2 to the power n. Space complexity is auxiliary stack space of big of n. Now we saw that there were overlapping subproblems. Yes, we saw that there were overlapping subproblems. And how did we saw that? If you remember, we started with a very big problem. We've started with the entire array, then we reduced it to small, then we reduced it to small. So the problem was broken down into sub-problem, 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 and eventually solved with a single base case. So thereby, the sub-problems, if you are breaking down the problem into sub-problems, they are bound to repeat. And thereby, what can I apply? Memoization. Yes, thereby I can apply memoization. Now let's think about the memoization. What did I say? How will you apply memoization? The first trick is figure out the changing states. So there is an index and there is a target that might change. There is an index and there is a target that might change. So assuming the constraint says target will be lesser than 10 to the power 3, assuming the constraint says this, and assuming this is also something like this, the constraints. So index you will take as 10 to the power 3 plus 1 more, because there is something as 10 to the power 3. So in order to have this as an index, you need to plus 1 multiplied with target of 10 to the power 3 plus 1. So this is the DP array that you will be requiring. And you know how to memorize. I have already taught you that. By the way, this will be a Boolean DP array. This can be a Boolean DP array because the function is Boolean. So you just need to return a true or false. So what I can say is, okay, DP of index target, and if DP of index target is not equal to, by the way, Boolean you can't take, you have to take true and false. So -1 and return DP of index target. So you can't take true and false in the memoization. So you can't take Boolean, you have to take an integer. For memoization in tabulation, you can take true and false. Why? Because you know -1 is marked for any unvisited state. So how will you determine if you mark true and false for the unvisited state? So it's very important, -1 is marked. This is how the memoization solution will look. And the memoization solution is very simple. The time complexity will be n crossed target, and the space complexity will be n crossed target array, and an auxiliary space of bgo of n, which is an auxiliary space complexity which we have to reduce. And that can only be done by tabulation. So the next step is tabulation. Let's quickly check that out. So how do you write the tabulation? I've already taught you the steps. How do you write the tabulation, guys? First step is declare the DP array of the same size, n and target. So please declare the DP array of the same size. Once you have declared the DP array of the same size, what's the next step? Next step was to figure out the base cases and write it. So just without thinking anything, go to the recurrence and see what are the base cases. The recurrence says any moment the target is 0. Any moment the target is 0, you return true. So if target is 0, what can be the possible value of index? Ask your brain, what can be the possible values of index? 0, 1, 2 till n-1. So for every 1 on 0th index, you return a true. So just write it. Don't think anything else. Just go and write. Tabulation, you should not complicate. You should keep it simple. For I equal to 0 till n-1, you write DP of I, target is 0, equal to true. That's what you did right in the base case, because for every index, if target is 0, you write true. So just write it now. What are you waiting for? Let's look at the next base case. The next base case says if index is 0. So index is 0 for sure. Return true if it's equivalent to target. So index is 0 and target can be anything. Okay. But when will it be true? When will it be true? For every target, what can be the possible values of target at index 0? Think, ask your brain to think. You'll be like, it can be anything. Target can be 0, target can be 1. It can't be 0, but it can be 1, it can be 2. It can be till any value of target, the given target. So you'll be like, but which guy will be true? Only A of 0 will be true. In DP of 0, A of 0 will only be true. Realize, no matter what the target is, if it's equal to A of 0, then only it will be true. Everyone else will be false. So initially you can mark the entire DP as false. So can I say only DP of 0 and A of 0 will be true? I can. So basically I can be like, okay, the next base case is if DP of 0, array of 0 is true. Why? Very obvious. I am saying at index 0, can I form this target A of 0? And the answer is yes. Because at only on the A of 0 array, you can form a target A of 0. You can't form apart from that. So these are the base cases. First step done. Next step. Form the nested loops. How many states are there? 2 states. Index will be 1. The other one will be target. Where does index start from? Go and look at the recurrence. In the recurrence, index was n-1, n-2, n-3 and so on till 0. Top down. Top down. What's bottom up? What's bottom up? Ulta. 0. 0 to ho chuka hai. 1 till n-1. Correct. 1 till n-1. Perfect. What about target? Target went on. From target, you started with the eventual goal. You moved till 0. Over here, what will happen? You go opposite. Yes. So you go opposite 1 to target. Because 0 has been already done. 0 has already been done. So this is what you do as nested loop. So without thinking, just write the nested loops. See how simple it is. Try the tabulation. I equal to 1 till n-1. Target will be, you can call it as the J loop in order to maintain easy. Let's write the target as 1 to whatever. Let's assume the target is K. So 1 to K. Perfect. Good. Now copy paste the recurrence. No need to do anything. Just copy paste the recurrence. So I'll show that when I code. So now it's time to code and then we will talk about the space optimization as well. But we just need to copy paste the recurrence and we will show that in the code because it becomes a lot easier. But only 2 steps you have to remember. Write the base cases. Just think of the base cases. Then just think of the nested states. Remember, the number of states is equal to the number of nested loops. It goes as simple as that. The number of states is equal to the nested loops. And the nested loops in the opposite fashion. From base case to the up. Bottom up. Base case to the up. So if you remember the recurrence tree, the base case was 0 to 3. Right? The base case was target was 2 to 4. Bottom up. So make sure you write it bottom up. Base case. Bottom up doesn't mean 0 to 0. Whatever means whatever is the base case, right there from whatever was the recurrence call. So I've written the tabulation concept and we just need to write the recurrence. So if you write it, the time complexity will be n into target again. And the space complexity will be big O of n into target, but there will be no auxiliary space. So I'll show you that by writing. So I've given the array, the n and the k. So we know we have to write the function. So we will write return the function. The target initially is the index n-1 and the target is k and there is an array. So we'll just write this off and let's write the function. Let's keep it the function as boolean function int index int target and we know the vector int and an array, right? So what are the cases? If the target is 0, we return a true. Simple enough. If the index is 0, we return array of 0 equal to target. And there can be a not tick case, so you can write boolean not tick saying I'll not tick, which means I'll go back with the same target and the array. There can be tick case, which is initially false, and I can only take the array of index. If that's lesser than target, then only I can take it. So let's assume I take it, then in that case f of index -1 comma target will reduce by array of index and I'll go till the array. And at the end of the day, I can return the take, not take. And that's what you do. So let's quickly run this off. So it does run fine, but we need to apply DP. So please apply DP. So write vector int and a DP, and we can definitely take it as n+1 as I said, vector, and the other thing will be vector int and you can take the target as k plus 1 and minus 1. By the way, n plus 1 is not required. You can take n also because you're starting from n minus 1, but the target has to be k plus 1. So I've taken this. Now you can just pass on the dp, and over here let's copy paste this portion. This will go over here and it will be the reference, and just make sure you pass it over here. Make sure you pass it over here as well, and make sure before returning you write dp of index and target to it. Remember, boolean will be 0 and 1, so it will automatically convert that into an integer. So, and over here, if dp of index target is not equal to minus 1, you can return it to dp of index and target. Okay, that's how you can do it. And now let's quickly run this off. Does run fine. Let's submit this. So you can see that it is running absolutely fine and we get 100 marks. But we don't need to stop here. We need to make sure we write the recurrence. So the recurrence was saying, let's write the first base case which is target equal to 0. So you can say int. By the way, now you can convert this into boolean because we don't need any minus 1 now, because minus 1 for memorization check, but we don't need that over here. So I can go as 0 and I can be like, we can go until I plus plus, and I can say dp of I of all the target zeros will be true. Let's write this. The next thing will be dp of 0, which is the next base case, and on only array of 0, yes, and only on array of 0 we will be having true. So why don't we write that? Simple. Now what are the couple of things? Index and target. So please make sure write it. Write index equal to 1, index goes on till n, and index plus plus, but the target starts from int target, will go on from 1 and it will go on till target and I plus plus, not target, it will be k and I plus plus. Perfect. Just copy paste the recurrence. Don't even think of anything. Just copy paste the recurrence. Copy paste the recurrence. Instead of f, make it dp of index minus 1. Perfect. Target. Amazing. So that's it. And over here you can just omit this portion. Take as false, and it will automatically make sure it only takes if it's greater, and again make a dp. Just change the recurrence. Yeah, just change the recurrence. No need to do anything else. Don't overcomplicate. As I always say, don't overcomplicate. Okay, done. Just remove this written. So if you remember, what did you call the function as? You call the function as f of n minus 1. So dp of n minus 1 and the target, which is k. So just now I'll just run this off and see if this is running fine. Okay, we did miss something. What did we miss? Okay, this will be vector of boolean, by the way. Okay, another mistake. We will be having target over here. We will also be having a target over here. So let's quickly check this off. That is fine, right? Works fine. Let's do the summation. Wow, runs fine. So what's the next step? Space optimization. And I told you space optimization is possible whenever you see something like that. What did you see? Index minus 1. The moment you see index minus 1, your eye is like, oh man, this is possible. Yes, this is possible. So we can definitely space optimize this. But something we need to take care is, remember this always, something we need to take care if we space optimize this is, I'll take the iPad and explain you. So if you're space optimizing, because I told you that when can we space optimize? We can space optimize if we have a state as I minus 1, because first time we always write the index 0, right? We always take the index 0, and in this index 0 some a of I will be marked as true. Then we go to index 1, then we compute this. But over here, if you carefully observe in the base case, yes, if you carefully observe in the base case, for every index, for every row, the 0th index is marked as true. So please make sure whenever you take a row, whenever the row is cur, this will be previous, right? Whenever the row is cur, the 0th index is marked as true. Always, every time you declare a row, the 0th index should be marked as true. That's a thumb rule, because in the base case, if you see, all the indexes are marked. So you compute the this. Once you have completed this, next you will move to the next one, and this guy will become previous. Now this guy will be cur, and it just uses I minus 1, the previous state. So whenever there is a case of previous state, the concept of previous and cur comes in. Again, I'm not going into depth because I've been teaching that from the last 12 lectures. So if you have not seen the previous lectures, it's your fault, not mine. So please make sure you go back and watch those lectures in order to understand space optimization in depth. So what did I say? I require a couple of stuffs. I require 2 rows to be stored. One is the previous, which will be of size target, that is k plus 1 0, because we just need to store the row. So the row will be having k columns. So that's what I need to store. That's what I've stored. And I also require a current for the current guy. So that's again k plus 1 and 0. Perfect. What is this? dp of I of 0. So I don't need this any further. But I know one thing. Previous of 0, the first guy will be true, and the cur of 0 will be true. Because for anyone, the target 0 has to be true. So for everyone, the 0 will be true. And over here, dp of 0. So instead of dp of 0, it's the previous one, because it's the previous one. Now we come to index of 1. What did I tell you? Index of I minus 1 means previous. Index of I minus 1 means previous. dp of index means current. Whenever this is completed, the previous is now current. And at the end, n minus 1 is the previous or current. Run this off. Let's quickly run this off. Runs fine. What is the time complexity now? It still stays the same, n into target. But what is the space complexity? The space complexity has now boiled into just bgo of target, and we are not using any index array. Just bgo of target is helping us to solve this problem in just bgo of k space. That's amazing. We're not requiring a 2D array. So remember this concept of previous and k. Whenever you see I minus 1, it's just you need to store the previous row. Just see what are you computing in the previous row. So if you're facing a problem in computing the previous row, what I'll recommend is just go back and do a dry run of these for loop and fill the table step by step, and you will slowly see in the table this row helps you to get this row, then this row helps you to get this row, then this row helps you to get this row, then this row helps you to get this row, then this row helps you to get this row, and ultimately the answer is stored here. Fill the table, run the for loops, do it yourself. Okay, I just can't spoon feed everything. Do it yourself, and you will slowly realize space optimization is the easiest thing in the world. It's just using couple of rows and just swapping every time. So I hope you have understood the first problem on DP on subsequences. So just in case you did, please make sure you like this video, and to continue our tradition, in the comment section, please make sure you write an understood so that I do get motivated that you're understanding the explanation of the problems. And yeah, if you're new to this channel, please do consider subscribing to us, because we do put a lot of DS Algo content. You can check that out on our channel. And yeah, with this, we'll be wrapping up this video. Let's meet in the next one. Till then, bye-bye. Take care.
Whenever your heart is broken.